This video lesson starts with a general description of the electromagnetic spectrum and follows it up with a detailed description of each part. This chart is similar to many that you'll see in textbooks. If you've got a physics examination on waves, it's quite likely that you'll have to know most of the stuff on here. As I've drawn it, on the left-hand side are the longest waves, radio waves. They're long waves, but they have the highest frequency. They're called radio waves quite naturally because these are the waves that radio signals are carried by. At the other end of the spectrum are the short waves, gamma rays. They're short, very high frequency. The names of the waves really come from how they're produced rather than exactly the wavelength. For example, there's quite a big overlap between X-rays and gamma rays. If you have examination in this subject, one of the key questions you're likely to be asked is, what are electromagnetic waves? Why are they grouped together? What is it they've got in common? Well, they're all transverse waves. They will all polarize, refract, diffract, interfere, and they will exhibit the Doppler effect. They don't need a medium or material to pass through. They'll all travel at the same speed in the vacuum. That's 300,000 kilometers per second. And very importantly, they are all produced by rapidly oscillating electric charges. Just before we start the detailed description of each part of the electromagnetic spectrum, let's just check that you understand the connection between velocity, frequency, and wavelength. You can jump forward a couple of minutes if you do. Unless they're travelling in a dense medium, all the waves will travel at the same speed. That is usually given the symbol c, the speed of light. And that's about 300 million meters per second. So if we run through a couple of examples, let's start with radio waves. Now we define those as a group of waves running from several kilometers long down to as little as a meter, perhaps even less. But if we take 1 kilometer or 1,000 meters as an example, then from V equals frequency times wavelength, V equals f lambda, the speed is c, remember the speed of light, equals f lambda. Rearranging that, we have frequency equals speed over wavelength. That's 3 times 10 to the 8 divided by 1,000, which gives us 3 times 10 to the 5 hertz. So 2 more examples. We'll start with microwaves, and we'll take an assumption of a wavelength of 3 centimeters, that's 0.03 meters. Doing that in the equation, we finally get a frequency of 10 to the 10 hertz. Last one, gamma radiation. But this time we'll work in the opposite direction. Gamma radiation has a typical frequency of 10 to the 19, maybe 10 to the 20 hertz. So if we work backwards, we can calculate the wavelength. The rearranged equation is that wavelength is equal to speed over frequency, and that finally gives us that wavelength of 3 times 10 to the minus 12 meters, which, to give it a context, is less than 1/10 the size of a helium atom. The properties of electromagnetic radiation vary gradually through the spectrum. We're going to look at those properties, the uses, and, where appropriate, the dangers of these radiations. Starting with radio waves. Now that includes those that are used to transmit television signals. This is a typical transmitter. This one is in fact Emily Moor, which is in Yorkshire. Like most transmitters, it is, where possible, put on the top of a hillside. But of course, that is not always possible, and one of the major advantages of long waves is they will diffract around an obstacle like a hillside. Illustrating this, the waves spread out from the transmitter. The wavelength is long and constant, although that might not be drawn very well here. As it meets an obstacle, the wave diffracts or curves around the back of that obstacle. So a receiver, which would normally be in the shadow of the wave, can still receive a signal. Not all waves will pass through all of the atmosphere. This diagram illustrates which waves will pass through which parts of the atmosphere. You can see that long radio waves are blocked by the upper atmosphere. The shorter radio waves will pass through the atmosphere. This is a very important property for long-distance transmission. Long radio waves will, when transmitted, reflect from the upper atmosphere, from the ionosphere, and this means that they can be received a large distance away around the curvature of the Earth. Shorter radio waves, including those used for television program transmission, will not do this. They will pass through the upper atmosphere, and therefore they are only suitable for transmitters which are reasonably close to the receiver. Terrestrial radio and television programs are transmitted from a metal aerial and, as you no doubt know, are received on a metal aerial on the roof of buildings. The waves are produced in the transmitter aerial because electrons are made to oscillate up and down. These produce the radiation, which spreads out and is intercepted by the receiver aerial, where the waves make the electrons in that aerial oscillate up and down. The television amplifies these waves and then interprets the signal as picture and sound. Electromagnetic waves with wavelengths between about 300 and 3 millimeters are usually described as microwaves, although as mentioned before, this is not a precise definition. The microwaves used in a microwave oven have a wavelength of about 100 millimeters. These are absorbed by the fat and water in the food and convert to heat. Because some of the microwaves will penetrate the surface, the heating is inside the food, which makes the cooking very efficient. The other major use of microwaves is in communication, mostly point-to-point communication, remembering that microwaves are short and therefore don't diffract around obstacles particularly easily. They're often transmitted from dishes at the top of tall aerials, or maybe they are put on the top of already existing tall buildings. Microwaves have a short wavelength. They have wavelengths of under 30 centimeters. When transmitted, therefore, and hitting an obstacle, they don't diffract significantly behind the obstacle. So any obstacle is likely to create a shadow behind it. This explains why in a hilly area you're not likely to get a very good telephone signal, unless of course you're on top of the hill. Microwaves are particularly useful in transmission to and from satellites. Looking at this diagram, you can see that waves in the range down to about 1/3 of a meter can pass through the atmosphere. That means that communication to an overhead satellite in a straight line is straightforward. Communication satellites are in a high orbit above the Earth's surface. The satellites rotate round the Earth at the same speed as the Earth is spinning. This is a geostationary orbit. Because the satellite is always in the same position relative to the Earth's surface, it enables the transmitting dishes and the receiving dishes to always point in the same direction and receive the signal. Finally, we must not forget that radar is a major user of microwaves and was, in the development in the Second World War, the vehicle by which microwaves were first used and exploited. Infrared radiation gets its name from the Latin prefix infra, which means just below. It has a frequency just below that of red light. That is a wavelength just above that of red light. Infrared radiation was first discovered when a thermometer was placed just by the red of a spectrum. The thermometer went up, the temperature seemed to go up, but it was something invisible making that happen. We can make infrared visible to us by using an infrared camera, a camera sensitive to that radiation. Here there are two cameras strapped together, looking at a toaster, here, and then a hot plate. The one sensitive to infrared is showing bright white. whereas the other, sensitive only to visible light, is either dark or dull red. The same infrared sensitive camera looking at a remote control shows a very bright light. Using this sensitive camera, the light is bright enough to show up a face, a truly scary experience. More sophisticated infrared cameras can show longer wavelengths of radiation and interpret those as different temperatures. To summarize, we can also call infrared heat radiation. It can be detected on our skin, particularly on our faces and our hands. It is the method of heat transfer from toasters and cookers. The small amounts of long wavelength radiation transmitted from surfaces which are merely warm, such as these, can be detected by security lights and burglar alarms. And as we've shown, infrared radiation is used for short distance communication, for example, in remote controls. Infrared radiation, visible light, and ultraviolet radiation are produced in similar ways. That is, by electrons jumping between energy levels within the electron shell of an atom. The excitement can be caused by heating. The electron jumps from one energy level to the next, and then as it falls back, it emits the electromagnetic radiation. Visible light is a tiny portion of the whole of the electromagnetic spectrum. So why is it that we see in this small range of waves? Returning to the graph which shows which waves will pass through the atmosphere, you can see that visible light is one of the few wavelengths that can. The atmosphere will block much of the other wavelengths, so there is very little of them coming from the sun by which we can see. Some infrared radiation is available, but because infrared rays are longer, the detail to which we could see would be less. Of course, species adjust to the conditions around them. There are insects which are out in the bright of the day when ultraviolet light is available that can see in this range, in the ultraviolet range. And there are animals which hunt almost always at night, including some snakes, which can successfully detect infrared radiation and use that to hunt for their prey. Most people associate ultraviolet radiation, or UV, with getting a good tan, and that's quite right. Part of the UV spectrum causes a brown pigment to be created in the skin. The body produces this brown pigment to help protect the skin from the damaging effect of ultraviolet radiation. Although, slightly ironically, we do need some ultraviolet radiation exposure in order to produce the essential vitamin D in our skin. We're exposed to ultraviolet radiation because a small proportion of the UV in sunlight can penetrate the atmosphere, and ultraviolet radiation can be produced artificially. The problem is that it can cause ionization within an atom. If a pulse or photon of ultraviolet radiation enters an atom, it may have enough energy to knock an electron right out of that atom. The remaining atom is charged or ionized. If that atom is within organic material, such as a skin cell, then that cell may die, causing sunburn, which, as you know, can be very uncomfortable, not to mention painful. However, even more seriously, if that atom is within the DNA of the cell, then it may alter the cell, but the cell continues to grow. That can cause a cancer, in this case, skin cancer. We can turn this property of ultraviolet radiation to damage living material to our advantage. We use UV as a sterilizer. For example, hairdressers often put their tools into a UV cabinet to sterilize, to kill all of the bacteria. And similarly, water can be sterilized by shining UV light through it, killing the bacteria within it. Some chemicals will fluoresce when exposed to ultraviolet light. That is, the ultraviolet light is absorbed and visible light is emitted. This property is exploited in nightclubs and in making standard fluorescent tubes. In these tubes, an electric current is passed through the gas. The fast-moving electrons carrying the current strike the atoms of gas within the tube and excite the electrons within the atoms. As those excited electrons change energy levels, they emit pulses of ultraviolet light. This hits the coating on the inside of the tube, which fluoresces, producing visible light. Lamps and tubes made to produce ultraviolet light are therefore the same as these, except without the coating on the inside. These lamps use the idea of fluorescence, for example the examination of banknotes, and for illuminating security marking on valuable goods. We all associate X-rays with the shadow pictures taken through our bodies to show our skeletons. X-rays are very penetrating. They pass easily through flesh, but are inhibited by the bones. These shadow pictures are not limited to our bodies. X-ray machines are widely used in airport security. In X-ray machines, very fast electrons are fired at a metal target. As the electrons hit this target, they are rapidly deaccelerated, and in doing so produce a pulse of X-rays. The fast electron may displace an electron already within the atom. Sometimes the fast electron comes in and knocks out the electron entirely, leaving a gap within the atom. The atom is briefly ionized. An electron then from the outer shells will fall in and take the place, the change in energy levels resulting again in a pulse of X-rays. Because of their high energy, X-rays cause even more ionization than ultraviolet. If you need medical treatment, then having an X-ray is a risk worth taking, but radiologists have to be careful to avoid excessive exposure. So whilst the X-ray is being taken, they move behind a protective screen. Using this property in another way, we can use the damaging effect of X-rays to our advantage. We use it to treat cancer. In a machine like this, either X-rays or perhaps gamma rays, because they have very similar properties, are aimed at the tumour. The machine is rotated around the body. The tumour is always in the path of the X-rays, but because of the rotation, the healthy tissue around it gets a relatively small dose. Gamma radiation is produced by some radioactive materials. It comes from the core of the atom. Gamma rays are often shorter and more energetic than X-rays, but there is a large overlap, and the definition of the difference between them is mostly in the way that it is produced. The nucleus of some atoms may be in a high energy state, particularly if the atom has recently emitted either alpha or beta radiation. That high energy state causes a rearrangement of the particles within the nucleus, and the energy released from that causes the release of a photon or pulse of gamma radiation. As with X-rays, gamma is a powerful ionizing radiation. This ability to kill bacteria makes it very useful for sterilizing surgical instruments. In many ways more useful than X-rays, because the source is small, light, and requires no power source. If the instruments are placed in a sealed pack and then irradiated, they will remain sterilized until the pack is opened. In wealthy Western countries, food is generally preserved by refrigeration. In areas remote from reliable power supplies, food can be sealed in a pack and then irradiated. Because the radiation kills all of the bacteria, the food can remain preserved for a very long period. The method is slightly controversial because we're not sure of the side effects. However, it may be that it is preferable to food poisoning. Another use of a gamma radiation source is to trace the flow of fluid through a complex system such as this. If a small amount of gamma-emitting fluid is injected into the system, because gamma radiation is very penetrating and will pass through the metal pipes, it can be detected anywhere along its route. Using the same ideas, the flow of fluids around the body can be traced. So as little as possible damage is caused to the body, the source should be weak and it should have a very short half-life. Thank you for watching.